Okay, thank you very much for letting me talk in the conference. And good afternoon, my name is Idit, and I'm a PhD student at the Faculty of Civil and Environmental Engineering at the Technion. My advisor is Professor David Brodai. And I'll be talking today about my first challenge in my PhD, which was dealing with missing observations in the data I was working with, data of PM 2.5 mass concentrations. Unfortunately, when we monitor air pollution, we almost always have missing values for reasons like device failures or other technical issues. And the motivation to deal with these missing values is many times so we can perform a statistical analysis that requires a complete data set, such as metrics for factorization that is used in source apportionment, for example, when eventually we want to obtain a reliable data set so we can reach the right conclusions. And before the imputation, we should first make the right assumptions regarding the mechanism by which values are missing. And it is commonly assumed that the missing data mechanism in air quality data is missing at random, which is where the missing value is independent of the measured variable itself. And that was my assumption as well. So the database I was working with included measurements of PM 2.5 between 2000 and 2019 in a half-hourly resolution, and included 82 air quality monitoring stations, of course, all used EPA-approved instruments that are spread all over Israel. In general, Israel experienced quite high average levels of PM 2.5. All above recommended levels. Here you can see the annual mean levels in the biggest cities and areas. Previous studies had shown that a substantial share of these high concentrations are due to transboundary transport of PM carried to Israel during certain synoptic conditions. For example, we get a lot of dust from North Africa or the Arabian Peninsula, but also sulfates from East Europe during summer conditions. Here's just an example of an extreme dust storm over the Middle East in 2015. So in the first stage, I tried to take a certain subset of the entire database for practical reasons. This is a temporal coverage of all 82 AQM stations in the 20 years that I had. And so I focused on a subset of 59 stations. The white is where I have measurements and red when I don't have. So eventually I took a subset of 59 stations and their measurements between 2012 and 2019. So here you can see a snapshot of my data table with the missing values in it. Just an example, where each row is an observation in time and each column is a station. And some approaches for imputation of those missing values, we treat each column as a standalone time series and use only the data from that column to fill in the missing values. Other approaches would see here a multivariate data set and also try to exploit the special relations that exist within the data. And multivariate KNN, k-nearest neighbors, was my approach. Of course, KNN is a simple and very not new algorithm. In its most basic form, it means just finding for each missing value in an observation. Let's say that this is my missing value, the k most similar non-missing observations. So if this entire row is an observation, this is the missing value. And for example, my k parameter is 2, and I find that these two observations are the most similar to this row, to this observation, then I will somehow average the 15.6 and 15.1 values and obtain an estimate for my missing value. So this is the basic form, and to that basic form I added some unique improvements that improved the estimation. This included the first was a weight that is based on the inverse distance between observations, and it gives preference to rows with more measured values in them. Of course, they were more reliable. And the distance itself, in the distance, I've used an Euclidean distance, but I also added a correlation between column J. Let's say that this is my column J, the column of my missing value. So the correlation of MJ would be the correlation between this station and all other stations. And that way, when a certain observation in a station J was imputed, stations with high correlations with the imputed station J contributed more to the calculated distance. And I called my custom KNN method WKNNR for weighted KNN with correlation. And the third addition was to account for adjacent observations. That is, I added the forward and this forward and backward time step offset of each feature or each station. So my data table was now 3 times larger. And that way, a temporal correlation in each station was embedded in the imputation. So technically, a univariate perspective was embedded in the multivariate method. And when the lag and lead observations were added as inputs to the model, the method was denoted WKNNR with LL for lag and lead. And as a benchmark to compare with my custom KNN, I took probably the most popular machine learning multivariate imputation today, the Miss Forest algorithm, where the basic idea is to model each feature, each station in my case, as a function of all other stations, and then use my trained model to estimate the missing values in that specific feature. And it does so in an iterative way, so it's fine-tuning the estimation in each iteration. I've used the Python implementation from scikit-learn library that uses extremely randomized decision trees as the regressor. And this imputation method was denoted IIET for iterative imputation with extra extremely randomized decision trees. So the workflow was to first put aside a validation set comprised of chunks of different sizes that were artificially set as missing. The longest time window was 1 month and the shortest half an hour. And these are seen in the plot here of the temporal coverage of my 59 stations seen in red here. And then I tuned some hyperparameters of the iterative imputer, the extra tree estimator, and of course the K parameter of the WKNNR using cross-validation. And after tuning, I ran the 2 models, also with the additional input of the lag and lead values. And then I looked at the performance of the models on the validation set and eventually chose the best model. So at first, I manually looked at each of my 59 stations and examined their performance, for example, using a scatter plot of measured versus imputed for each of the different time windows in each of the models. So here you can see a comparison between IIET and WKNNR for 2 AQM stations, number 36 and number 4, and for 2 times long missing period, of course, artificially missing period, 30 days and half hour. And soon it was clear when I looked at scatter plots like that and looked at the RMSE and R square that the performance of the WKNNR, my model, was better in short missing data windows, and the iterative imputation was better in longer time windows. And after eventually examining pretty much each of the stations, I omitted stations with poor performance. Most of them were with poor temporal coverage to begin with. Many stations had more than 50% accumulated missing observations. And I was left with 31 stations I could now compare their performance in general together in each of my examined models here and in each of the time window sizes, looking at RMSE, at R square, mean error, and mean bias. And it was clear from these results that the addition of the lag and lead values improved the WKN and R model. If you look at the gray versus the green is much better, lower RMC, higher R square, especially in the short intervals. But in the iterative imputation method, when I added the lag and lead values, I caused a bias in general, less better performance, and specifically a bias. If I look at the red versus the white here with the lag and lead, the performance is poor. So clearly the best two options for W, KNNR with the lag and lead, and the IIET. On a closer look on some time windows that were used for validation, marked here as green background, I saw that again the IIET here in the red line better followed the measurements, which are in black line, in the longer periods again, and in the short ones, half an hour and 1 hour, the WKN with the lag and lead, the blue line was much better. And so eventually these two best models were combined. So I've used the imputed values from WKN and R with lag and lead in the short missing data intervals of 1 hour and half hour, and the IIT in the longer data intervals. And this ended in a complete data set of 31 AQM stations from 2012 to 2019, marked here in blue and spread all over Israel. And here you can see completed time series of station number 2, for example, where the red background were missing values completely and were imputed, and I had a complete time series for that station. So if I summarize, in this work, we've offered an improved multivariate KNN method that accounted for both spatial and temporal similarity in the data set. I think we also offered a certain imputation workflow that was proved to work well. Based on the set-aside validation subset, we examined the performance of our suggested model against a benchmark commonly used method, and concluded that the best imputation product for our dataset, but possibly for other datasets as well, could be obtained by combining the WKNR with lag and lead imputation for short gaps with the missing, with the IIET for longer gaps of missing data. It's important to note that most of the previously published air pollution imputation studies used external data, such as time, meteorological parameters, concentrations of other pollutants to enhance their predictions. And in this work, we demonstrated an alternative approach, which is accounting only for monitored PM2.5 from a network of AQM stations, and we achieved a pretty good imputation performance. So this approach can have an advantage if the imputed dataset is maybe used later in a further analysis, since we free all the other external data to be used as maybe covariates in advanced analysis. Possible improvements that we can think of course, accounting for longer lags and leads. It can potentially improve the results of the WKN R imputation in longer missing intervals. And possible another improvement is taking maybe a threshold for the correlation used in the imputation, maybe taking only the most correlated stations and not taking all stations as I did in this work. So also the data of the WKN, the model itself and the data I was working with are of course available on GitHub, and everyone are welcome to use it on your own dataset if you need. So thank you very much for listening, and if you have any questions, be glad to answer.
Thank you. I don't see any questions in the chat, but I have a question. Did you notice what stations correlated the best? What is your experience? Is there something like, are there some surprising results that the very distant stations correlate, and why would that be? Is there some confounding variable? Can you?
Yeah. So I don't have it, unfortunately. It's true. Yeah, I've noticed that most of the, of course, close by stations were the most correlated. But I had also stations. I think that it's interesting that also stations like that didn't have any stations nearby so much also had good performance. So it means that they might have correlated according to maybe I don't know if it's urban activity or something like that. So I think that the fact that I have also quite remote stations that had good performance in imputations means that it's not only a correlation that is nearby by distance.
Thanks.
If I answered the question, I hope.